Hello and welcome to the third video to help you with the Core 3 coursework. What we're going to look at through this video is the second method which you're going to be asked to solve the equations with. It's the rearrangement method. And we're going to do it again with, sorry, that isn't quite the equation I want it to be yet. Let's delete that actually. We're going to do it with the equation. We need to make sure that it's all proper, that it's equal. 0 is equal to x to the 5 minus 5x plus 3. Okay, this is the equation which I'm going to solve. Okay, if we look at the mark scheme, okay, Newton-Raphson, rearranging f of x in the form x of g of x, it's this domain here. Okay, so 1 mark, a rearrangement is applied successfully to find the root of the third equation. Okay, so let's just, for 1 mark, find a root of the equation using Newton-Raphson, the rearrangement method. Now, first of all, let's get the graph of it up. So, using our GeoGebra, we want to make that 1, 0, 0, 0. That one, that's minus 5, and that's plus 3. Okay, now let's decide, I tell you what, let's find that root again. Okay, let's find the root between minus 1, minus 2, and a minus 1. Let's find that root. So, the idea is, we've got 2 x's here. Now, for this method, the equation you pick for this method, it makes sense to choose an equation where there's you only see 2 x's. Here we've got an x to the 5 term and an x to the 1 term, okay, a linear term. So it makes sense to choose an equation where there's only 2. Now what we're going to do is I'm going to choose one of these x's. I'm going to choose the red x, and or no, in fact I'm going to choose the blue x. Okay, I'm going to rearrange it to make that blue x the subject. So first of all, I'm going to add 5x to both sides. So 5x is equal to x to the power of 5 plus 3. Okay, so I've just added that 5x to both sides. And then finally, to get it subject, I'm going to make x is equal to, well, this is going to be a fraction. So we're going to make it x equal to x to the power of 5 plus 3. Divided by 5. Okay, now this is the basis for our what we call our iterative sequence. Now what I'm going to do is I'm going to write this again to insert an equation, but this time I'm going to use some subscripts because this is going to make a sequence of numbers where the more numbers we take, hopefully it should take us closer to the solution. Okay, x. Okay, so this is what we, now I've just written this down. I'll put the n on the side where there's a function and the n plus 1 on the side where there's just x. Now this is a sequence, just like we learned in core 2. So all we need is, if we have a value of x to start with, we put it to the power of 5 plus 3, then divide by 5, then we'll get a second value of x, okay? So, for example, if I take my value of x, we start with x0. x0 is going to be 1, for example. That means then, it's gone a bit, make that a bit smaller. If x0 is 1, we get 1, x2 x1, the next term in the sequence, is going to be, well, it's 1 to the power of 5 plus 3, which is 4. 4 divided by 5 is 0.8. Okay? The next value we're going to resubstitute in 0.8 to the power of 5 this time. So 0.8 to the power of 5, I've got a calculator handy here, plus 3, and then I divide by 5, and my new answer is 0.665536. No, 0.665536. Okay, and we can go on and on. Now, this could take a while, so we're going to use Excel here, and we need to pick a good starting value as well. Now, the root which we want to find is between -1 and -2, so it makes sense. Let's make a starting value of -1. So, here is our iterative formula, which we're going to use. Let's get that up there, and let's see how this works on Excel. Now, what we're going to do, before we have, for the change in sign, we had an x and an f of x row and column. What I'm going to do now, I'm going to mix it up a bit. I'm going to have an n column and an x. Now, n represents the number of iterations. So we start off with 0. I don't know why it's gone like that. There we go. There we go. So this is the number of times we do it. Okay. And we want to start off with, because our root is close to -2 and -1, let's make it equal to -1. Okay. So my first value is -1. Now, to get the next value, I need to substitute that -1 into this equation. So, using Excel, I'm going to do this. Right, now I'm going to be really careful of the brackets. I've got a fraction and do the numerator first. So, brackets. This is the numerator bit. And inside those brackets, I need an x to the power of 5. So, I'm going to do double brackets, that to the power of 5, close brackets. Then I'm adding the 3. So, it'll be add 3. Close brackets. So I've got all that numerator done. Now we can just divide by 5, divide by 5. Okay, I get a new value. Okay, now if I drag that down, Excel will do it all for me, lovely jubbly. Now what do we see here? What do we see here? Right, now you can see that after the 13th iteration, let's go here. After the 13th iteration, they are repeating itself. Now, it would change, obviously, a bit if we had more decimal places, but we've got this to 9 decimal places here. So we have found a root to the equation to 9 decimal places, 0.618033989. Now, the trouble is, though, this constitutes a failure. We wanted to find this root here, but we have obviously managed to find this root here. Now, this constitutes a failure. And the question which we have to ask ourselves is why that is a failure. Okay? Now, the reason why it's a failure all lies in the form of our function here. Okay? So, how you can imagine this is, what we're trying to do is, the roots to this equation equals 0 are the roots where the graph of y equals x to the 5 minus 5x plus 3 and the graph of y equals 0, it's where those two lines or two graphs cross. Now, when it's equal to 0, that's not a problem. The line y equals 0 is just the x-axis, and we can make them cross. It's just where it crosses the x-axis. Equivalently, we could say, we've rearranged this equation, so this equation is the same equation as that, it has the same roots. We could say that it's where the graph of this graph and the graph of y equals x, it's where they cross as well. And I can demonstrate that by writing that down. So let's find, so y is equal to x to the power of 5 plus 3. Be a bit careful with my brackets here, because I always go a bit mental. X to the power 5 plus 3 divided by 5. Okay, and y equals x. Now look here. This is our rearranged one, so I'm just going to change the color here, just to make it clear. And this is our line y equals x. I'm just right-clicking. Where they cross corresponds to where the original equation crosses the x-axis. Look, where they cross corresponds to where the original equation crosses the x-axis. Where the blue line and the red line and the red curve cross is exactly the same places where the original equation crosses the x-axis. Okay, because all we've done is rearrange that equation into and simultaneous equations with basically y is equal to x, y is equal to this. For this one, it's like saying simultaneous equations, y is equal to this and y is equal to 0. The trouble is y equals to 0 is just the x-axis. Okay, so to explain why this doesn't work, let's get rid of that graph because that's causing the confusion. Right, so this is our graph of y equals x to the 5 plus 3 over 5, and the blue line is the graph of y equals x. Now, we started off with a value of minus 0.1. Okay, so let's get some lines there. Right. So what we did, we first of all found out the value on the graph there. Okay, so minus 1 to b, b has a value 0.4, which is what we found the first iteration to be. Okay, now what we construct here is what we call a staircase diagram, because our next value is going to be 0.4. Now 0.4 is there, which is going to be approximately, it's going to be going up to there, but the way we can do this, because the line is y equals x, we can just move that across to there, and our next value is going to be d, which we had as 0.6, and it's 0.602048. Okay, this is just, I haven't got it quite on the curve there. This is the problem with GeoGebra, not with the maths. Now we can keep on going. It gets very, oh, I have to zoom in. Let's just zoom in, not a problem. And we can zoom in further and further. The point being, you can see that if we start at minus 1, we're going to converge into, using this staircase, the root near 0.6. In this case, 0.618033989. This is a failure. Okay, we've done it wrong somehow. We haven't managed to get it to the root which we want. With the root which we want was here. Okay, now this is called a staircase diagram because you kind of make a staircase. The key is, the reason why this doesn't converge to the root which we want it to is because of the, if we look at where they intersect, if we look at the point G, the gradient of the red curve is greater than 1. It's greater than 1 because the gradient of the blue line is 1. The gradient of this curve is bigger than 1. So the staircase for this route is no matter what our starting value is, we're never going to converge to this route. Okay, we're going to converge to another route, or diverge completely, go to infinity or negative infinity. So because the gradient of this curve is less than 1, it doesn't work to this route. Now, if we take it into comparison with the route here, the gradient of this curve at that route, at that point, is less than 1. It's shallower than the blue line. Therefore, it will converge to that route, if it converges at all. Now, if we look at this one here, we haven't mentioned this route at all. This graph here is again bigger than 1. It's steeper than the blue y equals x line. Therefore, we're never going to be able to get it to converge to there. Okay, so this represents a failure. And fundamentally, and what you need to talk about in your exam, this is failure, or in your coursework, because g dashed of x, which is the gradient function, differentiation, is less than 1. Okay. And in fact, you can then prove that with this function. You can actually prove that because if well, sorry, let's define g of x. G of x is basically g of x is this function here. Okay. So if g of x is, get it in fractions, x to the 5 plus 3 all over. No, I knew that wasn't going to work. Annoying. Do this again. X to the 5 plus 3 all over 5. We know g dashed of x is equal to 4x, sorry, rubbish, 5x to the 4 all over 5, which is actually x to the 4. Now we know that root, which is going to be, let's say, minus 1.5, we know g of minus 1.5 in this case is going to be, well, it's definitely going to be bigger than 1. Okay. It's going to be bigger than 1. Okay, so there's failure. It doesn't converge to the root we want it to. So our rearrangement was incorrect. Okay, our rearrangement was the wrong rearrangement. So instead of doing it for the red one or for the blue one, I'm going to do it for the red one. I'm going to rearrange for the red one. So I'm going to first of all add 5x and take away 3. So we get 5x take away 3 is equal to x to the 5. And then finally I'm going to take the fifth root to get x. So just changing sides around, I get x is equal to 5x minus 3 to the power of 1 over 5th. Okay. This is going to be my new iterative equation. Okay. This is going to be my g of x. So if we write that again using subscripts, nope. And let's get that bit then again. Okay, so there's our iterative function. Now, I'm going to start from exactly the same place, and you need to do this in the exams as well. You need to make this start at exactly the same place. So we're going to start at if x0 is minus 1. Our function now completely changes, because now our iterative sequence is performed from this one. Okay, so it's going to be equal to, right, let's do this. So now I'm going to be mega careful with brackets here. 5 times the previous value, okay, minus 3, close brackets. Right, so I've got that bit. Now I need to do it to the power of, now I'm going to do it 1 over 5. Okay, now if I, first of all, let's get rid of these ones here. Drag this down. Yay! We can see that, there we go. It repeats itself again after 13 iterations to the correct root. This is the root we wanted to find. We wanted to find that one. We didn't want to find that one, but we managed to find it. Okay, I'm just going to get rid of some of that. Right. So we managed to find the root. With this arrangement was successful. Now to see that, let's get rid of that one. Let's keep the line y equals x, because remember, what we're doing here, the roots of the original equation are exactly the same as where the line y equals x and y equals this intersect. So we've got the line y equals x in GeoGebra. Let's sketch this graph and see where they intersect. So if I do y is equal to 5x minus 3 to the power of, now I'm going to do it in fractions. I wouldn't put that as 0.5. Okay, do not put, when you're doing fractional powers in GeoGebra, as decimals, put them as fractions. There is a good reason for that. Now look, we get the intersections. We have them there. We should have them. Where do they intersect? And it's crashed by the looks of things. It's a little grifter. What's happening here? Right, I don't know. Very unsure what happened there, if I'm being completely honest, but there we go. We've got three routes. This is the route which we're worried about. This is the route which we try to find. Now, this time, if we're showing, because you have to show this in the exam, you have to show it graphically how it works. If we do the staircase diagram, we started at -1, go to the graph. I want to try and make that a straight line. And there we go. Then we go to the line, then we go to the graph. You can see how that works, lovely jubbly. Eventually we're gonna mega lines, right. You can see how that's eventually going to converge into the route we wanted. Now the reason why this is, remember, is because this graph, let's color that red as well. This graph, at that point there, the gradient is shallower than the gradient of the line. The gradient is less than 1. It works because it's less than 1. Okay, so for this one, and this is what you need to write in the coursework, g dash of x is going to be less than 1. So we have success. Okay. Now to differentiate this, to show that g dash of x, okay, we actually need to use a method in core 3 for this, but it's not a problem. Here we've got a power. We're going to bring that power down just as we would normally. Okay, so 1/5. Okay. Now that becomes 5x minus 3 to the power of, now if we were taking 1 off a fifth, it would become -4 fifths. Okay, that's normal, but the trouble is we've got to multiply it by this, the differential of what's inside the brackets. Now if we differentiate, this is what we call the chain rule, which we'll come across in a lot more detail next year. But if we differentiate this, we get 5, because 5x differentiates to 5, so we have to multiply it by 5. 5/5 is just 1, so our different g dashed of x is this. And you can now see that if we put g dashed of minus 1.618, which is what we got it as, 1.618, you can show that that is going to be less than 1. Okay, that's less than 1. Okay, so that is effectively the rearrangement method. Let's have a look at the criteria here. So a rearrangement is applied successfully to find the root of the third equation. Convergence of the rearrangement to the root is demonstrated graphically, and the magnitude of g dashed of x is discussed. Right, we talked about that. A rearrangement of the same equation is applied in a situation where the iteration fails to converge to the required root. Now, we actually did that first, but it doesn't matter which order you do. The first rearrangement didn't work, but the second arrangement did. The failure is demonstrated graphically, and the magnitude of g dashed of x is discussed. Okay, so no mention on error bounds. It's always a good idea to have the error bounds, though, because what we've got here, we've got x is equal to -1.618033989. Now, we actually want it to 5 significant figures, because that is what the other ones are going to be too. So it's actually that with 5 significant figures. Bearing in mind we have to include the 1 this time. So to 5 significant figures, it is that. Therefore, The error bounds are going to be that, and if it's a symbol, I need a plus or minus symbol here. Don't want wingdings. Okay, let's not waste your time. So plus stroke minus 0.00005. Okay, so there's our error bounds as well, really important. So there's the solution of the equation with the error bounds, and once you explain it graphically and you mention d's aster of x, you get all of the marks.